Greetings. So, we are discussing essentially steady state electromagnetism as of now. So, steady state means that things our properties are independent of time, and we discussed steady currents in our previous class, currents which are not changing with time. What is changing with time nevertheless is the position of the charge, because it is the flow of charge which constitutes the current. So, you have a volume current over here which is going in a region of space which has got all the three dimensions as you see in this. It may have any kind of shape suggested by this curved surface over here. And you have a volume current which is flowing in the direction of this arrow, and the dimension of this solid block which is in the direction of the flow of the charge is what I call as delta L parallel. And the two dimensions which are orthogonal to this direction are delta L perpendicular 1, and this is also delta L perpendicular. It is also orthogonal to the direction of the charge flow, and that is what I call as delta L perpendicular 2. All right. So, this is the cross sectional area of these two orthogonal dimensions, which is the product of delta L1 and delta L2, both being orthogonal to the direction of propagation of the charge. And the current itself is charge delta q by the time interval over which the charge moves, that is what constitutes the current. And I multiply and divide by the volume element, by a tiny volume element which is delta V, which is the product of these three dimensions, of which delta L parallel by delta T is nothing but the speed at which the charges are flowing. And here delta q by delta V is nothing but the volume charge density, which in the previous class I had represented by rho, but now I represent it by xi, because I want to reserve the symbol rho for resistivity, which I will be using shortly. Okay? So, I am now going to represent the charge density by xi rather than rho. So, this is the relation that you get for the volume current density, which represents the current per unit transverse area. Okay, the area, the cross sectional area is both the sides have got the subscript perpendicular, and it is the transverse area transverse to the direction of the flow of the current. Okay, and then in terms of this, you pick up the direction of the current, and you essentially have what is called as the current density vector. So, you have this current density vector, which is the volume current density, the current per unit transverse area, and you can see that it has got the dimensions of the charge per unit time. So, that is the current per unit area which is crossing that cross sectional area. So, the dimensions of the current density vector are L minus 2, T minus 1 and Q. So, let us look at a few other physical parameters and look at their dimensions. Like if the current is flowing in a conductor, so the conductor has got a resistance. It will not allow the current to flow without offering some resistance, unless it is a superconductor or an ideal conductor with zero resistance. And this resistance is proportional to the length of the conductor and inversely proportional to the cross sectional area over which the current flows. And the proportionality is what you call as the resistivity. Okay? So, the dimensions of resistivity you can determine quite easily from this. So, it will be ml to the 3 t minus 1 q minus 2. Okay. So, this will be the dimension of resistivity. It is also represented in terms of the conductivity, which is just the inverse of the resistivity. So, resistivity is the proportionality which tells you which is the elemental property of the material itself, and the resistance depends on the size of the material, how long this material is and what is its cross sectional area. So, those properties of course will change for any piece of conductor, but its intrinsic property, which is the resistivity, that is this proportionality, and its inverse is the conductance or conductivity. So, the dimensions of conductivity will be the inverse of the dimensions of resistivity. So, it will be m to the minus 1, L to the minus 3, T to the plus 1 and Q to the plus 2. All right. Now, we have seen the dimensions of the current density vector. It is L to the minus 2, T to the minus 1 and Q. So, dimensional analysis is a very powerful tool in electrodynamics. So, let us use it. We also know that the dimensions of the work done, which is the potential difference as you move a charge from one point to another, which will give you the voltage difference. So, this is ml to the 2 t to the minus 2, which are the dimensions of energy per unit charge. Okay, that is the energy expended to move a unit charge, to move it from one point to another. Okay. So, this is the voltage difference, this is the work done in displacing a unit charge. So, if you compare this, you will see that the dimensions of sigma times f and j, they suggest some sort of a causal relationship, causality in the sense that okay, there is a certain cause and there is a certain effect. Okay. That there is a voltage difference is the cause, and that a current flows is the effect. Okay. So, this is not causality in the sense in which we talk about it in Newton's second law, which is F equal to dP by dt. There the cause effect relationship is that there is a cause, which is the stimulus, and it has got an effect, which is the change in momentum. All right. So, dP by dt is the force. So, that is not what we are talking about, but there is a similar kind of situation here, that there is a voltage difference as a result of which the current flows. Okay. So, it is some sort of a cause effect relationship, and you can see from this dimensional analysis that the current density vector is sigma times E. Now, this is what tells you how matter responds to electric fields. So, if you place a charge in an electric field, it will electric field is generated because there is a voltage difference between 2 points, and as a result of this voltage difference there is a causal effect, and that results, it manifests in the flow of the charge, which is what the current is. Okay. So, this is a relation which is often called as a constitutive relation, because it tells how matter responds to fields, and there are these constitutive relations even in fluid mechanics and in electromagnetic theory. So, how does the charge respond to an electric field? It moves and constitutes a current, right. So, so you have got this relation J equal to sigma E, which, as you will see very quickly, is nothing but the Ohm's law, which was known as an empirical law and you can write J equal to sigma E. Sigma is often a constant, but depending on the properties of materials, some materials have got different properties, anisotropic properties in different directions. It may have one property along x axis and a different response to the electric field along the y axis, in which case the conductivity becomes a tensor rather than a scalar. So, it will depend on the directions as well. So, the current itself is the surface integral of the current density. It is the current per cross sectional area, as we have seen, right. And if you go back to the Ohm's law, that there is a work done which is a voltage difference in moving a test charge from point A to point B per unit charge. So, that is the force exerted by the field, which is the electric intensity, because it is per unit charge, and you can immediately see that I equal to this sigma A over L delta phi is nothing but the familiar Ohm's law that we write usually as V equal to Ri, and it is some sort of a stimulus response cause effect kind of relationship, and which is why Feynman calls it as Newton's law of electricity, okay, because it has got the same spirit, although it is not talking about the rate of change of momentum, not in that sense. Okay, so this is the Ohm's law for linear conductors, and then you have more complex materials which I will not talk about. So, you may have a nonlinear response, you may have a conductivity which is a tensor, and you may have some terms which go as quadratic or other powers of the magnitude of the electric intensity, which will determine. So, what happens if you place this conductor in an external field? All right. So, as soon as you place the conductor in the electric field, the positive charges in it, if they are free to move, they would move along the direction of the field, but positive charges in materials are embedded in the nuclei. The protons are in the nuclei, which are somewhat immobile, and they do not really move, but the electrons are less massive, and they can be easily displaced. They have much smaller inertia. So, they are the ones which move in the opposite direction, but it does not matter whether the positive charge moves in the direction of the field or the electrons move in the opposite direction. What happens is that there is a charge imbalance, and that is what constitutes an instantaneous sort of movement of the charges, but this will not keep happening. These charges will not keep happening, because the moment this happens, the displacement of the charges depletes the right hand side in this figure of the negative charge, which becomes effectively positively charged, and then there is an electric field in the opposite direction, and as a result of this, you will have a cancellation, a tendency of the internal field to cancel the external field, and this will happen till the field inside the conductor itself goes to 0. After that, this process would stop. Now, this is a very rapid process, and when this is happening, we do not have steady state electromagnetism. You have some time dependent variations. We are talking about the steady state electromagnetism. So, what happens after this steady state is attained? Now, this happens very fast, and we are discussing here what happens after the steady state is attained, and notice that once the steady state is attained, not till then, once it is attained, the electric field inside will be 0. Okay? The electric field will be inside 0, but only if the resistance is 0. Okay? if the resistance is not 0, then we have already seen that the Ohm's law operates, and you have, if the relationship between the current density and the electric intensity is given by the Ohm's law, which is J equal to sigma E. Okay? So, J equal to sigma E is the constitutive relation, which is the Ohm's law, and this does not come in the family of relations that we call as Maxwell's equations, because it tells you how the system responds to fields. So, it is a constitutive relation which you must add to the family of equations which we are acquainting ourselves with as Maxwell's equations. And when resistance is not 0, the electric intensity cannot be 0, because you need a force to keep the charge moving, because the resistance has to be overcome. It is like having this object move on this surface. Even if I want to move it at a constant velocity, it cannot move at a constant velocity unless I apply a force, because I have to overcome friction. So, resistance is that frictional force which is opposing the movement of these charges. So, now we know that the electric intensity inside the conductor would go to 0, all right. This is nothing but the gradient of the potential. So, the surface of the potential will therefore become an equipotential, and it will change only in a direction orthogonal to the shape of the conductor, whatever it is. Inside the conductor, the intensity will be 0, and the gradient of the potential being 0, the potential itself will be essentially constant inside the conductor. So, these are some immediate conclusions that we can draw from this. And we have seen from the Coulomb-Gauss law that we have discussed earlier that the divergence of E is rho over epsilon 0, and since the intensity E itself is 0, it means that the charge itself inside the conductor will be 0. So, where is the charge? It will go and spread. It cannot be inside, and that is what you would expect. If you keep some free charge inside the conductor, then all the like charges repel, and this repulsion will keep happening till the energy of the system is minimized, and that will happen when the entire charge has spread to the surface. Okay? So, the entire charge will go to the surface, there will be no charge inside, and if you take any Gaussian surface over which you can evaluate this Gaussian surface integral E dot ds, which is entirely inside the conductor, then this surface integral will essentially vanish, and the intensity itself must therefore be orthogonal to the surface at each point of the conductor. So, we will do one or two small exercises just to develop some comfort with this situation. So, we are given a conductor in this exercise in which you scoop out some cavity, okay, just take it out, and inside that cavity you put some charge, and just for the sake of specific discussion, we will assume that the charge that you have put inside is a positive charge. You can put negative charge as well, and then everything that we talk about minus and plus will be reversed, interchanged, but we will just for the sake of discussion put a positive charge. And we also place a charge uppercase Q on the conductor, and we are now asking where will this charge be, what will be, how will we describe its distribution on the system. So, there is a small charge, lowercase charge, lowercase q, which we put inside the cavity, and an uppercase Q on the conductor itself in this cavity. So, this is the picture that we have, right. And if you now construct any Gaussian surface here, okay, then the surface integral of E dot ds over this must go to 0, which means that the charge that it encloses must go to 0, out of which there is a charge plus q over here. And to balance that, there has to be a minus charge inside this Gaussian surface. Okay? And unless that extra charge is exactly minus q, you will not get the total cancellation plus q and minus q, giving you a net 0. And this Gaussian surface can be anywhere. It can be very close to the cavity, just snugly enclosing it, or away, stretched out, snugly touching the outer surface. Wherever it is, this result has to hold good, because the electric intensity in the conductor itself must vanish. Okay? So, this negative charge of course has to come from induced charge. So, the process of induction is very straightforward, because the conductor is a neutral material, but it does have both positive and negative charges in equal number, which is what makes it, neutral on a macroscopic level. But it has got these free electrons in the conduction band, which are free to move, they are mobile, okay? And they move so that they will be inside this Gaussian surface, but it has to be any Gaussian surface, including a Gaussian surface which touches the cavity snugly, which means that the negative charge has to be right on the inner surface of the cavity. It cannot be anywhere else, okay? Because if it is not snugly touching the cavity's inner surface, if it is outside, then you could construct a Gaussian surface between that charge and the cavity, and then the plus q and minus q would not cancel each other. So, the Gaussian surface, since it can be any Gaussian surface, this total negative charge will have to be induced right on the inner surface of the cavity. Okay? But now what is the charge on the conductor? You of course have plus q which is placed on it, so we will worry about it in just a moment. So, we have not touched that as yet, but now the conductor itself has got a minus q charge which is on the inner surface of the cavity, which cannot come out of nothing. Okay. This is not a part of the plus q charge that you have placed there. That is a positive charge, this is a negative charge, that could be positive or negative of course. But this is a negative charge, and this has come from the movement of the charge, and effectively the outer surface would be depleted of this charge and will have a plus q charge, which will be on the outer surface along with the plus q charge that you have placed extra. So, the charge neutrality of the conductor requires that the plus q charge will be placed on the outer surface. Okay? So, this is how the charges will be distributed. So, you will have an inner charge minus q on the inner surface of the cavity. You already have a charge q, then you have the electric intensity to be 0 in the conductor, and the plus charge including the uppercase q and the lowercase q, which will cancel this induced charge. So, the plus q and the minus q are induced charges. They have not come out of nothing, they are already there in the neutral material, but they have only been displaced, minus q to the inner surface of the cavity and plus q to the outer surface of the conductor. Okay? So, that is how the charge distribution has taken place, and this is going to happen no matter where you place the cavity. The cavity can be toward the right or left or up or down, you can move it anywhere as long as it is inside, some material inside the conductor that you have scooped out. It does not depend on the shape of the cavity. We have a completely arbitrary shape. It could be spherical, rectangular, or it could have the shape of a rat, if you like, or do not like. All right? It could be any shape, it does not matter. So, it also does not depend on where inside the cavity the charge plus q is placed. You can put it right in the middle of the cavity if it has got some geometrical shape, if it may not even be geometrical shape, so it really does not matter, then there is no symmetry point. So, it could be to one extreme, up or down or left or right, all right, or forward or backward, any which way, anywhere in the cavity you put this. So, the cavity is really doing wonders. So far as the field outside is concerned, it does not matter what is happening inside the cavity. The charge you can move around, you can place it there, but the Gauss's law would still be valid. Okay? So, the cavity essentially isolates the electrostatic phenomenon inside the cavity from whatever is happening outside, and these two are completely independent of each other. So, the external field does not penetrate into the cavity for the same reason. So, the disrespect is mutual, all right, and the induced charges keep external fields off from getting into the cavity, which is sort of nice, because if there is a lightning and you are sitting inside a car, then you are in a caged shell. So, you will be quite safe, nothing will happen to you because of this phenomenon, because you are insulated from the outside electric fields, and the field directly due to the charge inside the cavity is also, it does not have any effect outside. So, here is another situation where you have got a spherical conductor and you cut out a cavity of some arbitrary shape anywhere in the spherical conductor, and inside you place a charge q anywhere inside that cavity at no particular point of symmetry. The cavity itself does not have to have any symmetry, it may have some symmetry, it does not matter. But then notice that what it will do is it will induce a charge minus q on the inner surface of the cavity and a charge plus q on the outer surface of the cavity. What is inside the cavity is insulated from the outside world, and the outside world would only experience the charge plus q which is on the outer surface, right, and that field, it will generate a field outside this sphere as if the whole charge is concentrated at the center. Okay. So, for all practical purposes, all the electric phenomena which are occurring outside this conducting sphere with a cavity inside with a plus charge inside will be exactly the same as if the whole charge was concentrated right at the center, although that is not the physical situation, but it does not matter. Okay. The electric intensity distribution in the region outside R would be exactly the same. So, now if you have a conductor which is charged, okay. So, we know that the intensity of the electric field inside the conductor is 0. We know that the charge has spread to the outer region. There is a certain charge density which I denote here as sigma. So, this is not the conductivity sigma, this is the charge density. So, I am going to use the same symbols again and again for various things. Rho for resistivity, rho for the volume charge density, sigma for the surface charge density, sigma for conductivity, and then the context will tell us what is what. Okay. So, the charge spreads to the outer surface, and you have the Gauss's law, which is the Coulomb-Gauss law, all right. And if you apply to a tiny Gaussian, this is sometimes called as a Gaussian pillbox, because old people like me, we we put our medicines in these tiny boxes, hoping that we will not forget to have it at the right time, and then set the alarm, and there's a very elaborate mechanism to handle this. But if you have this Gaussian pill box, it is just an imaginary closed surface, and you have this closed surface such that it straddles the surface of the conductor. Part of it is beneath the surface of the conductor, part of it is above the conductor, and over this cell, this Gaussian surface, you evaluate this surface integral E dot ds, then it will be given by the Coulomb-Gauss law, which is 1 over epsilon 0 times the charge enclosed, and the charge enclosed by this Gaussian surface is nothing but the charge density multiplied by the surface area element itself, right. So, once you go into the conductor, there is no intensity, right. So, the only contribution to the E dot ds will come from the part of the surface to which the electric field is orthogonal, right. If it is so that is the only thing which will contribute, because the electric intensity is orthogonal to the surface. So, that contribution will be equal to sigma delta s over epsilon 0, and the intensity itself therefore is the size of the surface element does not matter, it gets cancelled on the two sides of the equation, and this intensity is now given by sigma over epsilon 0. So, you can actually determine what is the electric intensity if you are given a surface charge density, right. How will you evaluate it? How will you determine it? If you have some way of either evaluating the potential or the intensity, some experimental method of determining this, then you know that the intensity is minus del phi by del z, that is the relationship between electric intensity and the potential. Then from a measurement of either the intensity or the measurement of the potential, you can determine the intensity, and once you know the intensity, then you can determine what is the charge density at any given point, all right. Otherwise, for an object which has got an awkward shape, there is no easy way of determining what the charge density will be, because it will be more concentrated at the sharper edges and spreads out elsewhere. So, you can get the charge density by carrying out some measurements. If you have a charged conductor which you place in an electric field, then it is going to experience a certain force, right. Just like you put a point charge in an electric field, it experiences a force. If you have a conductor on which you have placed a charge, and we can determine what this charge, what this force will be like. So, we first determine the force per unit area, which is the charge times the electric intensity itself, and you can see that it depends on the surface charge density. So, it will be surface charge density sigma times the area of under consideration, which is delta s, and the external field in which you have placed this conductor. And you can do a small trick to determine what this external intensity will be like, because that external intensity will be not only because of the external field that you have applied, but it can also come from the charges elsewhere on the surface of the conductor. So, they are all adding up. The intensity that is above a tiny patch is because of the charges outside that patch, and also because of any external field. So, if you look at the intensity above the patch, it will be the external field plus sigma twice epsilon 0 over n, and this will be sigma minus external field minus this, right. And since below the surface the intensity is 0, right. So, you can determine this intensity to be sigma over twice epsilon 0 times the unit normal to the surface, because the intensity has to be orthogonal to the surface, and the force on the tiny area, which we know is given by sigma delta S times this external intensity, and external intensity is sigma twice over twice epsilon 0. So, you put it over here, and that tells you what is the force per unit area, because then you just have to divide this by delta S. So, the force per unit area is nothing but the pressure. So, what is happening is that the moment you place a charged conductor in an external field, it experiences an outward pressure, as if something is pushing it from inside, move away, all right. So, that is what is going to happen, and the physical dimensions of that conductor will tend to expand because of this pressure which is generated. Okay. So, in some sense this is an electromechanical effect, and to what extent it will impact its dimension depends on the actual magnitudes of the external and the internal forces. So, because there will be a competition between that. And notice that you have got a sigma here and another sigma here. So, this pressure goes as the square of sigma. Sigma is the charge density, and since the pressure goes as the square of sigma, it does not matter whether the charge is positive or negative. So, whether you place a positive charge or a negative charge, the effect is the same, that there is an outward pressure. The direction of the pressure is always outward. It is not that okay, if you put the opposite sign of the charge, it will tend to get compressed. No, it will tend to expand. In both cases, it will tend to expand. That is the pressure that the conducting material will experience, irrespective of the sign of the charge. Okay. So, we now talk about the potentials generated by a charge distribution. You have a charge distribution is in a certain region of space which has got some arbitrary shape, not just in 2 but in 3 dimensions. Okay. So, this is not just a surface, but a 3-dimensional object. You are seeing one face of it, and any point in this region where the charges are located is called as the source point, all right, which I will designate by the symbol r prime. And outside this, there will be a field which is generated by these charges, by this distribution of charges, which I will call as the field point. And I am asking what will be the field generated at that point due to a charge distribution over here, and that field is the negative gradient of the potential. So, I would ask what is the potential which is generated over there due to this charge distribution. So, this is the question about potential at a field point due to a charge distribution which has an arbitrary shape. It can also be a uniform charge density, it may be a non-uniform charge density, parts of it may be positive, parts of it may be negative, it does not matter, all right. And so, we are asking what will be the potential at a field point r due to a charge density rho at the source point r prime. So, you obviously have to divide this charge, which is the charge density times a volume element, divided by distance, which is the Coulomb's law, and integrate over the entire charge density. So, this is like the continuum hypothesis we have used in fluid mechanics. So, when you talk about these volume elements where you have a charge density, and the charge density is also like a Dirac delta function, all right. So, you are not talking about tiny volumes which are as tiny as you will really have to talk about the structure of an atom. What is the size of the nucleus? What is the size over which the positive charge is spread? Those are not the dimensions we are looking at. We are looking at matter in the continuum limit, okay, so that these sizes are small enough in comparison with everything else that is there in the geometry, but large enough so that you don't have to get into the details of the atomic structure itself. Okay? So, this is the continuum limit in which, so this is nothing but a superposition of the Coulomb's law for all the charge elements. Okay? You can write this difference vector r minus r prime as capital R prime, if you like, and rewrite the same expression in terms of the uppercase R prime. And notice that the vectors r and r prime are connected, the tips of these vectors are connected by the vector r minus r prime. And what comes into their relationship comes from the elementary result that you are familiar with from your school geometry, that if you have three sides of a triangle, then these sides are related by this quadratic representation. Okay, when this angle is 90 degrees, this relationship reduces to the Pythagoras theorem. But otherwise, you have got the cosine of the angle between these two directions, the direction toward the source point and the direction toward the field point, which is the cosine of the angle. And I have put a prime over here because it is going to change for different points inside this, which is why I have to carry out an integration over the primed volume element. Okay? So, now let us do a little bit of simplification. So, you can extract r square as a common factor from this, rewrite this, and now you have this term which offers yourself a method of developing an approximation, because you get the term r prime over r, and r prime will have a certain maximum value because the source charges are spread over a certain finite region of space. So, no matter what your origin of the coordinate frame of reference is, if you go far enough, there is a farthest point and the charge is not beyond that point, whereas the field point can be anywhere. Okay? So, if you go far away from this source distribution, that the denominator r becomes much larger than the numerator r prime, you can develop an approximation scheme between using this ratio r prime over r, because higher powers of r prime over r will become diminishingly small. So, you introduce a factor epsilon which becomes small in the limit as in the asymptotic limit that the field point is far away. Okay? So, this is the r square into 1 plus epsilon, and the 1 plus epsilon, the r itself, the r prime itself will be the square root of this. It is coming in the denominator, so it goes to the numerator with a minus sign, and now you can expand this in various powers of epsilon, keep track of the coefficients and keep track of the signs of the terms, right. And once you do that, you have got a power series expansion, and you can see that epsilon is a relatively small quantity if the field point is sufficiently far from the source. If not, it is not a small quantity and you cannot ignore it. But if you have got a charge distribution which is over a small region of space and you are interested in the electric fields, at other end of an experimental situation, then you can decide that I need to reconcile with the second power of epsilon but not the third, or with the third power of epsilon but not the fourth, and if you ignore the fourth, then you can obviously ignore the fifth and the sixth and all the higher powers because they are even weaker, right. So, that is how you develop approximation schemes, and you have this expression for the potential. Essentially what you are doing is you are expanding 1 over r in an infinite power series in epsilon, which is such a series that higher powers of epsilon become diminishingly small. Okay? So, you can work out these details and work out these expansions. It is a good exercise, so you certainly have to do it. So, I am not going to derive each terms, but of course, I am going to share this file with you. So, I'll give you a PDF of this, so you can check if you are right, or of course, if I have made some mistake. It will be my opportunity to learn from you where I made a mistake, and then I'll be glad to stand corrected. And if you do find any mistake, please do let me know so that I can correct it. So, you have got this 1 over r expansion, and epsilon is this term. So, once you go to far away from the source region, this expansion involves powers of epsilon, but epsilon also has got the cosine theta. Okay? It is the cosine of the angle between a source point and the field point. The source point is not the same. So, for this field point, the source point can be here, 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 right, wherever the charge is distributed. So, which is why you have to integrate over the variable r prime, okay, so that you can add up everything. So, it is just the superposition. So, you have got these number of terms, and which will have powers of r prime over r and also powers of cosine theta. Okay. So, here is some straightforward rearrangement of terms, which I am going to let you work out for yourself, but I will give you the final result, and then I will also give you a PDF of these slides so that you can check the intermediate steps. But I do not want to spend time doing that, because there is no big physics in it, there is no big mathematics in it. It is just rearrangement of terms. You move one term from here and put it here, and pick up another term from here, add it to this, because then you bring it to a form which is convenient to handle algebraically. So, that is all there is to it, nothing beyond your school algebra. Okay? So, you reorganize these terms, and you have this reorganization enables you to write it in terms of certain functions which are called as Legendre polynomials. So, you have got this cosine theta and various functions of cosine theta, like cos theta to the power 0, which is equal to 1, or cos theta to the power 1, which is cos theta itself, or you have cos theta to the power 2, which is cos square theta, but then it is scaled by a factor of 3, then you have 3 cos square theta, then you need to subtract 1 and then take half of it. So, that is the kind of functions that you will get from this rearrangement of the terms. So, once you make this rearrangement, the 1 over distance, 1 over r prime distance, which is the distance between the specific tiny source and the field point, right. So, that distance is written in powers of r prime over a r. Okay, you are summing over L going from 0 through infinity. So, it is an infinite series. Various terms will become diminishingly important, because for the same r prime, r is large and r prime over r to the power L become progressively smaller. And then there will be these Legendre polynomials. So, I have written the first few of these Legendre polynomials for L equal to 0, 1, 2, 3. So, you will you can get them from each other by using certain recursion relations, and this is something that you have either already learned or will soon learn in a course on mathematical physics. So, these are the Legendre polynomials. I definitely want you to plot them though. Okay? You must draw these figures by your own hand on a graph paper. Okay? Sketch the Legendre polynomials. I do not know if you have already done this in any of your earlier courses, but if you haven't, you must absolutely do it, okay, which is to plot the Legendre polynomials. They are functions of cosine theta. So, I represent cosine theta as x, and cos theta goes from -1 to +1. So, x goes from -1 to +1. So, the independent variable goes from -1 to +1, and for this you plot the PL of x for the first several Legendre polynomials. Actually, using those recursion relations, why don't you write a small program to calculate the Legendre polynomials for higher values of L, and write a small program also to generate the graphics contours of these, because I am going to make you use them when we discuss atomic wave functions, when we discuss the quantum mechanics part of this course. All right. So, you have these Legendre polynomials. You can represent this 1 over distance in terms of the Legendre polynomials, right. And if you look at the first few terms, which I have written out explicitly, I have also given them beautiful colors so that you can at a glance quickly pick them up. So, you have got the term corresponding for L equal to 0, which is a monopole term, because when you integrate the charge density over the entire volume, you are getting the total charge as if it is concentrated at the origin, which is why it is called as a monopole term. Then you have got the dipole term and the quadrupole term, and you can write this so this is the multipole expansion of the potential, and you have got infinite terms in this. We considered charge distribution, which was a continuous charge distribution. You may also have discrete charges, some of which are positive denoted by red and some as negative denoted by blue, in which case again you have to carry out a similar sum, right, and this is the complete equivalent analog of this multipole expansion of the potential due to a discrete set of charges, except that this has a discrete sum, whereas over here you had continuous integrations, but the integrations and the differentiations that we talk about are in the continuum limit, that you talk about volume elements which do go to 0, but not at the level of atomic structure. Okay? So, you have got these different terms. You can see that if in this summation you have got some positive charges and some negative charges, then this sum can actually go to 0, all right, because the positive and negative charges can cancel each other at some, depending on how the sum operates. So, similarly you have these, if you look at the dipole term, you can factor out the common direction of the field point and then get the net summation of charge times this distance from the source point, which is nothing but the electric dipole moment of, all right. So, you can have a corresponding analog over the continuous charge distribution, right. So, you have got this sum over dipole moments, which gives you the total dipole moment, which is whose analog for the continuous charge distribution is just this distance times the charge element, which is rho times the volume element, right, the volume charge density times the volume element, and then integrated over the whole region of space. So, it is really very straightforward, and you have got these this potential multipole expansion of the potential for discrete and continuous charge distributions coming out of it, taking very simple and neat expressions, right. So, if you have some regular arrangements, they are somewhat easy to write, because in this particular case, if you have got a a dipole of a plus and a minus charge, then the intensity drops at 1 over r square. If you have a quadrupole, then the intensity, not the intensity, the potential drops as 1 over r cube, and so on. So there are the simple relationships that you can develop. So you can write it in terms of the dipole moment or the quadrupole moment and so on. So these are typically tensors because they will depend on how these charges are configured and what is their shape and size. All right. So they have various tensorial properties, and in n dimensions you will have n to the power k components to work with. So the dipole is a tensor of rank 1, a quadrupole a tensor of rank 2, and so on. So you can write them in some equivalent forms, and essentially you have with you a complete infinite multipole expansion of the potential due to a charge distribution, due to a discrete set of charges, or due to the continuum charges. You can play with the geometry a little bit, ask yourself what happens if you change the coordinate frame of reference, what happens if you just shift the origin, because how does this respond to the choice of the coordinate system. If you change it, what will happen? And you can see that every Ri will be shifted by the displacement vector OA prime if you shift the origin of the frame of reference from here to here. And since this is coming in the explicit expression for the dipole moment over here, this will be the charge times this new displacement vector. So the dipole moment will actually change. Okay. So because of the choice of the coordinate frame of reference. So this is there is no physics in it. It's just a mathematical term that is added. But the potential distribution is what you are really interested in to carry out in terms of the experiments and so on. So you can determine what is the electric intensity at that point. Once you have the potential, you can determine the intensity by taking the negative gradient of the potential. You know how to take the negative gradient of a potential because you have got the explicit expression for the gradient operator in the various coordinate systems. So use a coordinate system that is appropriate to the geometry. So you might prefer the spherical polar system in some cases, or the cylindrical polar core system, or maybe the Cartesian, it does not matter. So use the one which is the most convenient one, and you can write the expressions for the electric intensity. And this is a dipole term, but it does not necessarily mean that you have two charges, one plus and one minus, which are separated. Okay? It is the dipole potential of the charge distribution, right? The charge distribution, it may have some plus and minus charges, spread out in the region of the source, and you may not be really talking about a physical dipole which is a plus charge here and a minus charge here. That's a physical dipole. The dipole moment that we talked about is a measure of the influence at the field point due to a charge distribution at the source. And at the source means at a given point. So you are really talking about a point dipole. All right. So this is what is sometimes also called as a pure dipole, and these two have slightly different shapes of the electric fields. The field lines is a popular idea. It has to be used with caution because it's not a very physical thing. So you can write the expression for the electric dipole using an appropriate coordinate system, and once you have written it, you can rewrite it in a form that is more convenient to you. Okay? So you have got a term in 2 cos theta, but it helps to write it as 3 cos theta minus cos theta. It's the same thing. But having done this, you can write it in a form which is 3 into the scalar product between the unit vectors along the dipole moment vector itself and the field point. Because now when you write it in this form, it is completely independent of the coordinate system. So, there is some advantage in doing it like this. Okay. So, this rewriting is a matter of straightforward substitutions, which is really convenient because you can it's always better to write your final expressions in a system which is independent of a particular choice of the coordinates. So, I will stop here for this class, and if there is any question we can discuss those. Yes.
So, we are considering a spherical conductor, and inside that conductor we are considering a cavity. Cavity is not in center, it is in almost near to periphery.
Okay.
And a positive charge is placed inside that cavity. Then we get a positive charge on the outer surface of our conductor.
Yeah.
Will that charge distribution will be uniform or non-uniform?
If it is a spherical conductor, it will be uniform, but it may not be a spherical conductor. If it is not a spherical conductor, it will not be uniform. Okay, because the charges are spreading out to minimize the total energy. Okay, see, the energy is 1 over distance. So, the closer the charges come, because it is in the denominator, the energy increases. The farther the charges go, the energy decreases. And the physical system tries to attain a configuration of minimum energy. So, it will try to minimize the energy and spread out uniformly. Any other question? Okay, so thank you very much.